In the late 1990s, SAP R3 solved a massive fragmentation problem by standardizing global enterprise operations, sales, materials, HR, finance, onto single, centralized relational databases. To handle thousands of simultaneous transactions, these databases were built using third normal form structures. This meant breaking data down into narrow, isolated tables, strictly optimized for fast, repetitive writes, what we call online transaction processing, or OLTP. The architecture worked perfectly for entering data, but extracting intelligence created an immediate conflict. Business executives required complex analytical queries, online analytical processing, or OLAP, that meant joining dozens of those isolated tables and scanning millions of historical rows at once. These two workloads collided. When a heavy analytical query scanned millions of rows, it locked the core database tables, causing total CPU exhaustion. Routine reporting actively sabotaged the business, and mission-critical activities like processing sales simply stalled. This crisis established a foundational rule for enterprise architecture. Analytical workloads must be physically decoupled from the operational database to protect business performance. SAP solved this by creating a dedicated specialized application server and repository, SAP Business Information Warehouse, or SAP BIW. The invention of the external data warehouse was a direct response to these physical hardware limits. It marked the start of a 30-year evolutionary chain in enterprise data architecture. Early SAP BIW established a structured data pipeline. Operational data was extracted from the source system, landed in a raw persistent staging area, the PSA, and then transformed into dimensional analytical storage. But storing that analytical data introduced a new bottleneck. Traditional relational databases used classic star schemas, which quickly led to massive dimension table explosion, as redundant master data was loaded in over and over again. This schematic shows SAP's structural solution, the extended star schema. You have a central fact table containing the transactional metrics, surrounded by dimension tables, but crucially, the master data is struct out and stored in its own distinct separate layer. To connect these layers without duplicating text, SAP generated integer-based surrogate IDs, or SIDs, and mapped them between the master data and the dimensions. This kept the database tables lean, but the architectural trade-off was brutal. Converting millions of operational keys into integer SIDs during nightly batch loads took hours, heavily restricting processing windows. Engineers successfully optimized query read speeds on disk-bound systems, but the highly complex physical schemas required to do so simply shifted the processing bottleneck from query execution directly to data loading. As these BW deployments expanded globally across enterprises, custom modeling led to brittle, entangled dependency trees and unmanageable delta processing errors. To regain control, SAP introduced the Layered Scalable Architecture, or LSA. This was a strict engineering framework designed to enforce a highly standardized sequential data flow across every enterprise deployment. This flow diagram maps the mandatory LSA physical staging layers. Raw data entered the PSA, was copied to a write-optimized data store object for rapid insertion, copied again to a standard DSO to manage delta changes, and finally aggregated into an info cube for reporting. Strict LSA compliance required organizations to physically store the exact same data across 4 to 6 different layers. The hardware storage footprint ballooned, and data latency increased with every sequential hop. The layered scalable architecture achieved the operational stability and governance large corporations needed, but it did so at the cost of extreme physical data duplication, pushing disk-based storage hardware to its absolute limit. The solution to disk-bound limits was to eliminate the disk. SAP replaced third-party relational databases entirely with SAP HANA, an in-memory, column-store database engine. This diagram illustrates the architectural principle of code pushdown. Instead of dragging massive datasets up into the application server for processing, analytical calculations and transformations were pushed down directly into the database layer. By executing parallel vector processing directly in RAM, the system bypassed mechanical disk reads entirely. The most complex workarounds of the previous decades were instantly obsolete. Physical database aggregates and batch SID generation processes were permanently eliminated. Moving to in-memory processing changed the fundamental laws of database interaction. By removing the physical limits of the disk, The architecture made legacy staging and complex physical schemas obsolete. To capitalize on this, SAP built SAP BW4 HANA. This was a streamlined HANA-native warehouse designed from the ground up, entirely stripped of legacy backwards compatibility constraints. The massive catalog of historical modeling objects was radically simplified. Decades of legacy data store objects and info cubes were collapsed into a single high-speed persistence layer, the Advanced Data Store Object, or ADOSO. The heavy physical LSA framework was replaced by LSA++. This modernized architecture replaced physical staging layers with dynamic virtual views. Objects like the composite provider now executed high-speed union and join operations natively in memory. You could combine vast datasets dynamically on the fly without ever copying or persisting the data. BW4 HANA proved that with massive in-memory compute power, enterprise data warehouses could finally stop physically duplicating data and start prioritizing real-time virtual abstraction. But the perimeter of the enterprise was expanding. Corporate data was no longer centralized on-premise. It was sprawling across multi-cloud environments like AWS, Azure, and Google Cloud. To manage this distributed reality, SAP launched SAP DataSphere, pivoting the architecture toward a new model, the Business Data Fabric. Attempting to extract and load petabytes of data from external hyperscaler lakehouses into a single centralized warehouse had become a costly engineering bottleneck. The monolithic approach was now an anti-pattern. This map illustrates the mechanism of zero-copy federation via smart data access. Instead of moving the data, DataSphere issues a remote query to an external cloud database, executes the calculation at the source, and retrieves the result without bulk replication pipelines. The architectural mandate had reversed. Instead of forcing all operational data into a central SAP repository, the system was now designed to leave data exactly where it resides, connecting it through a unified, federated fabric. This multi-cloud federation evolved into today's SAP Business Data Cloud, or BDC. It is an integrated AI-ready ecosystem encompassing DataSphere, SAP Analytics Cloud, and strategic hyperscaler partnerships. Modern organizations require open, multi-vendor data ecosystems to execute advanced machine learning and massive data engineering workloads. Historically, connecting SAP to external platforms meant spending months writing custom ETL pipelines. BDC replaces this manual integration with packaged SAP-managed data products. These curated business assets utilize open Delta sharing protocols to automatically ingest custom operational fields and share them directly with external lakehouses. This enables a dual compute architecture. Transactional OLAP workloads execute on SAP HANA Cloud, while advanced machine learning and Spark workloads execute simultaneously on platforms like Databricks, querying the same shared tables. By providing turnkey data assets, the Business Data Cloud solves the primary integration bottleneck. Data engineering teams no longer have to manually rebuild complex ERP business logic from scratch inside third-party platforms. Over 28 years, the underlying physical engines of enterprise data have been completely replaced, evolving from disk-bound relational tables to in-memory columns to open multi-cloud Delta lakes. Yet one element remained constant through every hardware upgrade: the semantic model. This is the abstraction layer that translates cryptic operational codes, like raw third normal form movement types, into legible business context. This timeline maps the unbroken lineage of that intellectual property. It begins with early business content and info objects, evolves into core schema notation, and exists today embedded within SAP-managed data products. Feeding raw, untranslated transactional tables directly into modern large language models and autonomous agents is an engineering error. Without semantic context, the AI hallucinates or fails entirely. Exposing SAP's historical semantic layer directly to enterprise AI agents solves this. It provides the exact currency conversions and complex organizational hierarchies, alongside row-level security provisions, required for the agent to execute autonomous actions securely. 3 decades of codified business semantics represent the true legacy of the SAP data warehouse. While the physical database structures have changed, these rules now provide the foundational knowledge graph for the AI-driven enterprise.